Next presenter on our list is Jack Chern. Jack can introduce himself.
Hi, do you hear me? Yes. I'll start out with a little background of how I got into the helicopter business. After a few years of working at the Martin Company and NACA, I wound up at the Air Corps at Wright Field, along with Hank Belkop, who I'm sure you all know, and Lou Schuler, who was chief engineer at command. We were a bunch of buck privates who were given project engineering jobs at Wright Field because I guess they were short of people. And I started at the prop lab with Hank, and then wound up in instrument flying training, so project engineer and instrument flying training. And I learned that the Air Corps wanted a helicopter trainer, much like what the Coast Guard had at Floyd Bennett Field. So I sent a Twix to the commander of Floyd Bennett Field, said a representative from Wright Field is going to visit your facility to look over your helicopter training. And I showed up in my corporal uniform and at Commander Erickson's office, and he looked me up and down. He said, "You're the representative of Wright Field?" I said, "Yes." He shooed me off to an enlisted person, and they showed me what they had. Years later at Sikorsky, I ran into Commander Erickson, and I tried to remind him of the incident, and he refused to remember. But that was my introduction to helicopters. Later on, I wound up at Sikorsky as Assistant Chief of Structures at Sikorsky, and that was really an education. This was 1946, and Sikorsky really was a wonderful place to work. This article about the great point-to-point race that Igor Sikorsky started to show that cars leaving the Sikorsky plant could get to Hartford, or not the cars, but the helicopter could beat a car or train or any other means of transportation. I learned a lot from Igor. I hope that this doesn't cause any concern, but he was a great person to be around. And one of the things that he was always doing was working with Serge Bablov on building new parts of his house. But one of the things that I heard this morning that surprised me was the reference to the VS-300 Sesqui tandem rotor. And I had thought that when I was at Sikorsky that Igor would never build another tandem helicopter. But we built one for him based on an R4 fuselage, and this was a proposal that we gave to the Navy, hoping to interest them. But this was 85% thrust in the main rotor, 15% in the tail rotor, which had a slight tilt to counteract torque, plus a real tail rotor to provide maneuverability. Sikorsky was generous, and I was very active in the Helicopter Society, and that they made a mistake of sending me to the 1955 Helicopter Society in Los Angeles. And while I was there, Ken Amer grabbed a hold of me and said, "Jack, how about coming out to see what we're doing?" And that was a mistake, because I wound up being in charge of helicopter development with Hughes for the next few years. And one of the first things we had to do was take Gish Jovanovich's rotor head and rotor system and design it into the 269 helicopter. And I learned a lot on helicopter development from Miller Watts, working closely with him for many years. And I took the S58 tail rotor bearings and put it as the pitch change bearings in the Hughes 269, and it increased the life and made it much more serviceable. But one of the things that we were concerned about was ground resonance. You've heard the word, probably you've never seen it, but you're going to see it in a few minutes. You'll notice that the landing gear was just a spring landing gear, no oleos. And this is a fully articulated main rotor. So that my task was to prove that you could use this kind of landing gear. I'll skip to the answer later and then show you the videotape I have of the ground resonance test. Here I am as a fictitious captain in the air in the Army with Gail Moore as the pilot in the landing gear, which we finally wound up using. But Gail was a pilot, and he was going to run this test on this rig, which was a hydraulically driven transmission, and this fuselage was free to move about. We had some tie downs as usual, and we'll look at the video. No, his pattern. Gail Moore was supposed to be the pilot, and unfortunately, in the middle of the test, he got the mumps and he had to stay away. And so I said, well, heck, I want to get the test over with, so I sat in for him. And it's fortunate that I did, because he was a good head taller than I, and I wore his helmet in here. And you'll see that when we got into resonance, the rotor blade just skinned the top of my helmet. If he'd have been in there, that would have been the end. We kept trying to develop ground resonance as we raised pitch and shook the stick. You'll see that somewhere along I think that's Ken Amer standing watching. Now, don't take your eyes off it, because it happens very fast. It happens when you're about 90% lift.
I don't think it's going to happen, Jack.
You know it does. This is a video that Ray... It happened. This is a video that Ray Prouty has made sure that all new employees at Hughes have watched.
Rewind it.
You want to see it again?
Yeah.
When I show it, I've got it twice on my tapes.
Oh,
Oh, hold it down.
that destruction took 1 2/3 seconds by counting frames.
All right, now let it go again. Notice he changed jacket in between those two shots.
Different day. If there are any questions.
Now that most of you come back at two administrative things, there's a list going around, attendance sheet. If you haven't signed it, see if you can find it in the back and someplace and sign it, and it's going to be typed up eventually. Another thing, you notice that we have a professional video maker over here who has been taking videos of everything except maybe the videos, which don't show up for you. This is eventually going to be edited, and it is going to be available to anybody for a slight charge, and that hasn't been decided yet. But if you would like to get your name on the shopping list here, leave a business card with my assistant over here, or just a slip of paper with your address and everything on it, and we'll get you on a list and tell you when this video is going to be available. The other thing, I have copies of many of the biographies of the people who were talking today. I had Rhett Flater asked me how many I wanted, and I said, well, I want at least enough to cover all of the pioneers, about 50, and he sort of blanched, but he did have 50 made. So I have passed these out to a number of you people who were on my engineering pioneer, or my pioneer list. After the meeting, come up here and pick up your copy if you didn't get one. If there's any left over, then that's for you non-pioneers. But I want to make sure the pioneers get these first. The next presenter on the list is George Brooks, who I knew many years ago when I worked on the Hughes XH-17. And
see if I can get this thing on so you can hear me. I bring you greetings from the Langley Research Center. It seems that everybody there has become immobile now, and now we've lost our carpenter. The only mobile person around there, I guess, who worked back in those days seems to be me anymore. So I'm real happy to be here, because Gustafson is sent his best wishes to everybody, but unfortunately he didn't feel healthy enough to join you. After I joined the Navy today after Pearl Harbor, and after 3 years in the North Atlantic and South Pacific, the Navy decided they'd send me back to schools to see if they could make an officer and a gentleman out of me. They sent me to Hampton-Sydney College, and when I got there, I met Bob Lynn, who was already a gentleman. And later on, we were transferred to Princeton, and Bob and I went through the system together. It was really a privilege to be there under the tutelage of Professor Nikolsky, really a fine gentleman. In 1949, I went to the Langley Research Center, And during that year, there were a couple of people from Hughes showed up. And I guess I had taken a course in helicopters and a course in vibrations at Princeton. And so I was chosen as the person to work with them. And what they were interested in was a dynamic model of the XH-17 helicopter. Now, I don't know if you remember the XH-17. Not very many of you saw it because it wasn't around very long. I'm pretty sure of that. But anyway, what the task was to build a model of that helicopter. Now, and when I'm talking about model, I'm talking about a complete aeroelastic dynamic simulation. Everything from the tires on up, where it was simulated. Because what they wanted to do was to use the results of these model tests to determine whether or not they could fly the helicopter. Well, somebody blindly gave me $12,000 as a budget and said build a model. So that's the model as a result of $12,000. Now the people who helped, their time wasn't counted in there. If you look at this model, you'll see, for example, that this helicopter has some very unusual properties. First thing, I used compressed air because we had 4 jets at the tips of the blade out here, and there were burners on the XH-17 helicopter, and the gas that was generated from the jets in the jet engines in the fuselage went up through the hub and out through the blades. Another very interesting feature of this helicopter was that it had straps here for the retention of the blades. These straps that went across and connected to the 2 sides. It had an unusual feature here. There was an inverted pendulum, which was spring-loaded so that if the hub moved relative to the fuselage, of course it was spring-restrained. Well, okay, let me show the next slide now. It had a lot, this will just give you a little better feel for the hub, and you can see the features that I was talking about. One thing that I could not do, of course, was to simulate the actual motions of the sparse plate. I had hydraulic pistons, but the lag and the lines were so high that the motion was faster than I could keep up with. So we used a new technique, the technique of tethering. Now that wasn't tethering to keep from ground resonance. The tethering, which you see here from these cables, were actually the cables that I used to control the helicopter. And I used them to bounce the helicopter around on the ground like you saw a while ago and everything else, trying to induce ground resonance if it existed. I never could get ground resonance on that helicopter model, so I think it was free. I think you could say that it was free of ground resonance. And the other problem they were concerned with was flutter. At that time, nobody had done any flutter analysis. I remember Langley, was famous for his work in flutter. And one of the things I did one day when I got interested in this was go talk to some of the flutter people. And the answer they gave me was, if you stop the rotor, come back and talk to us. Well, I said, gee, if I stop the rotor, I don't have a helicopter anymore. But that was the status, I think, of helicopter flutter about 1950. This shows the design of the blades. And the most interesting thing, or the most difficult thing for making this model was to find tubes that would carry this compressed air out to the tip jets, which had no stiffness and no weight and carried 85 pounds of pressure. Well, I made some, and they're still working. They worked three years ago when we tested them. And what I did was to take a piece of plastic that you run electric wires through, put it on a piece of pipe. I put some holes in the pipe so that I could put air pressure to get it back on. Put this plastic, I wrapped a piece of aircraft linen, cigarette fashion. That's what I called it in the report, if you ever read the report. And then I did a spiral wind in 2 directions. So it essentially weighed very, very little, but it was very, very strong and lasted, for a lot of years. And that shows the interior design Now this blade had two counterweights. One of them is, you can see out near the tip, and then there was another one which was inboard here. And that was primarily due to the fact that if you're worried about flutter, you know, you need to have your center of gravity of your blade or wing or what have you forward of the quarter cord. You couldn't do that with this design, so the counterweights were out at the tip and the end row to settle that issue. Okay, so we went into flying, and what was surprising, what this shows is that these two marks here are one per rev. It showed that we had a very large bending stress, free per rev, but very little torsional stress. And I remember them telling me, said, you got something wrong there. That can't be true. You don't get free per rev vibrations out of a two-bladed rotor. Well, there's free per rev vibrations, and there was a two-bladed rotor. Well, anyway, so by the time these tests were completed, Hughes was ready to do their test on their full-scale vehicle. They did a short flight. They came down and looked at the oscillograph records that they had, and they found exactly the same thing that the model showed. Then they came back to us and they said, well, gee, what can we do to fix it? So we went back, took the blade, went back and did tests outside of a wind tunnel, and then in the return passes of the full-scale tunnel, and the result came out exactly the same. And so far as I know, they told me that the helicopter had a fatigue life, estimated fatigue life for 5 minutes. Whether it ever flew again or not, I have no idea. I remember going out to Los Angeles a few times and seeing it sitting out on the edge. Why was this a problem? Here's the reason it was a problem. You see, we're operating out here. This is your normal rotor speed, and you can see you almost got a resonant condition between the free per rev flying and the blade bending, first to last blade bending frequency. And that was due, of course, to this value of the southward coefficient, as you recall, which is the thing that determines the difference between the natural frequencies of the blades when they're rotating and when they're not rotating. And that southward coefficient was such on those blades with the counterweights that it caused basically a condition of resonance there. At least it was high enough so that it got very high bending stresses in it. Well, so much for that. Maybe somebody else knows what finally happened to it. Then I took the model and I used it for several years for all kinds of research. And I got flooded, got plenty flooded. But, and you can see, for example, that if you look at the blade, various blade frequencies here, and you can see the buildup. Well, that was the incidence of flutter. And what I did to get the flutter, of course, was reduce the pitch stiffness. And of course, and when you have a system like that, the anisymmetric system is always more sensitive than the symmetric system because the bending is helping each other in each direction that you go. And the flutter that we got was almost cyclic blade motion. This flutter had, there was a couple of very interesting things that happened. First thing was that I needed to measure the frequency of the flutter, and I wanted to get a picture of it. And so I went over to the instrument people and I said, I'd like to take some pictures of a helicopter blade rotor flutter. And so they said, well, it'll take about 3 months to develop the system, and it'll cost something of the order of $3,000 for the instrumentation. So I went back and I got a piece of pipe and I drilled several holes in it, put micro switches in it, found the ball bearing, turned it loose at one end. As it went down the pipe, it set off the micro switches, fired the film as it went around, and I got the, I think it was probably the first major pictures of flutter that ever occurred. But it was a very interesting thing to do, and I enjoyed it. One of the last things I did before I went into space work was to, working on my doctoral dissertation, I had the feeling that this mechanical instability that you call ground resonance, if you had multiple degrees of freedom in your system, you'd have multiple degrees of instability. And that was what I set out to prove, and that's what I did prove with this model. And I did the calculations, the theory on it, And then I did the measurements and correlated those, and that's exactly what happened. So when you see these tall things sitting on the end of a wing, you know, don't forget, they are very good candidates for mechanical instability, which we call ground resonance, except that it can occur in the air. And your fuselage is basically acting as your ground, and you got your flexibility in your wings, etc. So now that was published in my doctoral dissertation in 1962. I was happened to have a couple of pictures here that I thought were kind of interesting. I'll just show you these. I saw these guys this morning all around these helicopters kind of close. And one you had a while ago kind of tickled me too. This happened to be a Pitcairn autogyro. I'm glad I wasn't anywhere close to it, I can tell you that. That of course was one of these cases of mechanical instability or ground resonance. Thank you, ladies and gentlemen.
Let me make a comment about the life of the A-17 blade. The man who would know the answer, unfortunately, Clay Boswell, died about 2 months ago.
Is that right? I didn't know. Well, I made a lot of other models and did, you know, over the years. I guess I worked in helicopters for about 14 years, and it was a fun thing to do. After that, I retired as the director of structures at Langley, but that wasn't any fun thing to do. I mean, pretty soon, when the research is gone, the funds were pretty much gone too, and that was what was really fun. Thank you.
I can't help but put a footnote on that. Those blades were originally designed to be bonded. This was 1947 or so, and they couldn't get the bonding technique right. So they decided they're going to rivet those blades. So they had 10,000 stress risers in there. And Clay Boswell would calculate how long that blade is going to last, and in the briefings for the flight, the pilot, Gail Moore, would say, is it okay? And Boswell would say, oh yeah, it's good for 10 hours, though he may have calculated only 15 minutes. But the flights were very short. They just went down the runway one way, landed, and towed it back. So, but unfortunately, nothing is left of that particular helicopter. It was just scrapped. This morning you heard something about the Cheyenne when Don Segner was talking about it. Al Yakler and I and Norm Gornberg are Cheyenne pioneers, and now Al is going to talk about his experiences before Cheyenne. Al?
Thank you, Ray. Before I went to Lockheed working on the Cheyenne, and Ray told me I shouldn't talk about it today. However, I worked at Kellett Aircraft. And Kellett has an interesting background in the helicopter industry. I just thought I'd review that for you, where Kellett, in the autogyro business, was trying to convert from autogyros into that of the helicopter business. And I joined them in 1946, working on a helicopter. And then it turned out that the last presenter that you saw talked about the XR-17. That was a program that started at Kellett in 1946. And my first job at Kellett was working on that XR-17. Young kid out of school, really had some challenging problems with that bird. So what I'd like to do first of all, though, is go back for Kellett and show you one of the autogyros that Kellett built, and they actually had operational experience on it. So on the next slide, this is the autogyro in operational use. It operated from the post office roof in Philadelphia, delivering mail to the Camden airport. And they actually had a very successful operational experience. I have some numbers here. I'm going to just read them to you. I can't... They had scheduled operational trips, 3,050. This is all in 1 year time period. Canceled trips, 443, represented about 14.4% of that. The trips that therefore were operated were 2,607. Now, all of that in a time period in 1939, they operated as an autogyro off the roof of the post office in Philadelphia, 30th Street Station. The failures for not being able to operate, most of it was because of weather. 286 cancellations were because of the weather. It amounted then to total trips that were canceled, that is, 443, 14.4%. The trips were delayed because mail was delayed. 393 of those trips were canceled because the mail didn't make it. So the aircraft actually performed very well as an operational vehicle in those days. I wasn't there at the time, but it's the history of Kellett Autogyro. So on the next one, as I mentioned, Kellett was coming away from the autogyro experience. And this is some background of other autogyros that were built in those days, showing what the future of the autogyros would be. On the next one was Kellett getting into the helicopter business. In 1943, they were awarded a contract for the XR-8. This is a syncopter helicopter. It was an experimental vehicle just to explore what the advantages of it were, awarded to Kellett, where Sikorsky had the single rotor with the tail rotor on it. And some people felt in those days that a syncopter would be more efficient. You don't have the tail rotor. This aircraft performed quite well. One of my first jobs at Kellett, when they were doing some experimental work, referring to that of ground residence, they had a procedure there of fastening cables to the bottom of the aircraft. And the people then were assigned at the end of these cables, if they got into a ground residence situation, you could see by the way the aircraft would vibrate, we were supposed to pull on those cables. I didn't know what we were doing at that time, and when I saw Jack's picture there, I said, I'm glad I didn't know. So this was the experience that we had trying to come out of the autogyro business into the helicopter business. The next contract that Kellett had was an award of the XR-10 aircraft. Now, in those days, the Air Force was interested in trying to carry cargo. So here we had twin engines, one on each side, and the cargo bay area was left clear so that you could carry passengers. This aircraft, again, was a syncopter, just a next version from that of the XR-8, and Kellett had a competition. They actually won the contract and designed and built this aircraft where it was going to eventually, in the eyes of Kellett, wanted to have a commercial version made. And I know the first time I went into the Kellett facilities back there in '46, they had a beautiful version of a commercial version, 10-passenger of this aircraft. On the next one then, there's the XR-17 aircraft that Kellett started before it went to Hughes. About the same time period, Kellett went into financial difficulties, and they had to try to save their company, and this is where they sold the rights and the actual hardware that we built on the XR-17 to Howard Hughes. The total contract, some of the people went with it. They finished it out on the West Coast as an aircraft, and as Ray mentioned, after it was designed and built, there were some difficulties. I must admit, this was quite a challenge for a small company like Kellett to take it on. So you can see the size of it. It's not by the model here. This is the real aircraft. And it was large enough to carry, supposedly, like the old lumber trucks had back in Philadelphia those days, to fly over an aircraft over the automobile and pick it up. Okay, and the next one then, Barney, is later on, Kellett wanted to get into an easier-to-fly aircraft, and they got an award of an experimental contract for stable Mabel. This was the term that was used for it, to experimentally evaluate handling qualities. We had a gyro on top of the aircraft, and this pilot then was to fly it, and he was able to fly it hands-off. It was a variable stability device where he could change the amount of stability into the rotor system for various phases. Back in those days, as someone mentioned earlier, we were told that in about 10 years from this time period, everybody was going to have a helicopter in your own backyard. Well, no way. So after this program here, it was not an engine on it, but we had rocket engines, little rockets on the tips of the blades, where we actually had an aircraft that was flying with hydrogen peroxide. Strictly an experimental aircraft, and didn't go anyplace except give us some knowledge on stability and control. This was the beginning of some thoughts for a compound autogyro. We added a wing and 2 engines on it. But this was the thinking that they had in those days for how to make a compound configuration operate. On the next one then, as I mentioned earlier, I went to work for Lockheed and got involved into the rigid rotor development at Lockheed. And when I joined Lockheed, they had already started to, by decree, and I'll say it that way, where the management of Lockheed gave the challenging job to Irv Culver to come up with a easy-to-fly vehicle where they thought at one time it was going to flood the market with low-cost, easy-to-fly vehicles for everybody's use. Well, we did, and the Model 286 was one of the first helicopters that we built, and it was easy to fly. We got it certified, and it was the first runner to that of an aircraft that went into a compound configuration and eventually into the Cheyenne that you heard Don Segner talk about today. At the same time, we were doing some experimental work on a stopped rotor configuration using the rigid rotor concept. In other words, the rigid rotor gave us a chance of looking not only at a helicopter with its good flying qualities, but also into a compound where you actually unloaded the rotor in forward flight and used the rotor then as an autogyro type rotor as a compound. And then also eventually a configuration could be done with a stopped rotor. On the next one then, the stopped rotor, the concept for the stopped rotor was to be able to fly it as a vehicle in a helicopter mode, go forward until 140 knots or thereabouts, where you could unload the rotor, stop the rotor, and then fly on the wing as an airplane, and you stow the rotor. In the next one, you'll show how this is the basic concept for it. the horsepower required on the first chart shows a typical helicopter horsepower required, and then you stop the rotor, as I mentioned, about 140 knots, and go down to a clean airplane configuration, and then go into an airplane mode, where in this case, we could go out to a speed of 350, 370 knots as a typical airplane. And we went through some design studies of this, actually building a rotor, putting it into the wind tunnel. The next one will show some of the test results of this rotor. We stopped and started the rotor in the Ames wind tunnel at 140 knots. I can't see the numbers from here, but it shows that at 140 knots, angles up to 12 degrees, and yeah. And it actually matched up with the predictions over here, where we are able to calculate what its performance would have been. We had successful starts and stops on this for 55 times in the wind tunnel. Successful starts and stops in folding the blades. Okay. This is what an operational configuration by an artist concept would look like, where initially we had it as a compound with propellers on it. Eventually, you could do it with a turbine engine and go faster. The concept lets itself unlimited in forward speed. It's a concept that we think would have an excellent potential even today yet. So in summary then, the lessons learned, we did in fact make an aircraft that was easy to fly. Some of the comments that we had from people that pilots that have flown it was that, this is military pilots, they said, well, if it's this easy to fly, the generals won't need pilots anymore, they'll go out and fly it themselves. And it was, in fact, I don't know whether you gathered from Don Segner's comments this morning, an aircraft that was truly easy to fly. It was very stable. It had a control power on the rotor system because it was a rigid rotor concept and highly damped. It had a high control power. I used to explain it that if you disturbed that rotor, if you were hovering, disturbed the rotor, it would go up and damp out very quickly, which made it the key to that of making a helicopter easy to fly. Even though in the early days, we were told that everybody was going to have a helicopter in their backyard in about 10 years or so, don't believe it. It's not necessarily because of the helicopter, but I think because of the operational use. I can't imagine seeing 1,000 helicopters flying over Montreal. The rigid rotor concept isn't new. Actually, the Autogyro started earlier with it and still used the term. When Kellett was working on the XR8 and the XR10, they had some difficulties with the blades. Actually, we used to call it inner smashing. They would actually contact themselves, and it wasn't a happy situation for it. But at that time, we were going to convert back to the rigid rotor and get rid of the flapping hinges, and that was at Kellett before Lockheed got involved. The rigid rotor, I think, has an excellent potential for a stop rotor configuration, and the stop rotor embodies some very inherent features to it, wherein it could operate as a compound helicopter or as an airplane or as the helicopter. It therefore means that it can be a vehicle that truly embodies the handling qualities of the helicopter as well as the speed and range and efficiency of a fixed-wing airplane. The forward speed is not limited as we have in as they have in the tilt rotor concepts today. And we have an ability to fly in two distinct modes, which means that if you ran into any difficulties, you can land it as an airplane or land it as a helicopter. And it embodies inherent features for stealth configuration. especially when it's in the airplane mode and you're folding the rotor. It can be made into a stealthy configuration. So just thought you'd like to know we did learn some lessons and implied them later on. Thank you.
As you know, we arranged the order of these presentations this morning by picking numbers out of a paper sack, and it turns out the next three presentations are all Sikorsky people. So Ed Katzenberger.
Ray,
Yeah.
I have 5 seconds.
All right.
I've got a photo here of Sikorsky's single blader
Oh, I've heard about that.
in flight. I don't have a slide, but people might be interested in looking at it. This was Sikorsky's approach to his folding rotor, of course.
I hope you're strong, Ray.
Yeah, okay.
Okay. Little difficulty, but not much. John, my son, is going to turn the view graphs. I'm really very happy to be here and all, and see so many old friends and friendly old competitors. I don't know whether they feel that way still, but I do. Maybe I'm optimistic, I don't know. What I'm going to do is tell you first what I was asked to do. That is, what was I up to 50 years ago? Not everything, just helicopters. And then I will go into something that what I think is much more interesting and significant, and that is what happened at the very beginning, between the very beginning and 50 years ago. I will not go into the present and tell you what glorious things Sikorsky helicopters can do now. John? I had these view graphs prepared because I thought there might be quite a number of you who do not recall what these helicopters looked like. They're so old now. This is the R5, the first one I worked on, which was, as you recall from this morning, was prepared as a design to be an aircraft to be placed on convoys during the war. You sat out in front there with nothing in front of you except some plexiglass. The footrests there could be converted into rudder pedals, and there was the collective to one side, and you could insert the stick. So if you wanted to, you could fly the aircraft. And that's what I did for a while back in 1944, showing that I had some feel for how this damn thing worked. As a matter of fact, the control forces were extremely high, about 20 pounds. We did not have servos at that time. And the other problem was with the first models, we did not have an offset flapping hinge. And therefore, the control response, aside from the control being very difficult to use, a control response was somewhat over-delayed, you might say. You'd push the stick forward, and nothing happened for a while. and then you would decide to push it a little bit further, and then the whole thing came up like this, and that sort of thing. It was rather difficult, and I really was amazed at our chief test pilot at the time, Dmitri Wiener, who could fly this thing aerobatically the way it was at first. And there it is. I contributed to the design, but the big load on the design of this was carried by one of the real pioneers, a fellow named Bill Hunt. I've been in contact with Bill. I had been in contact with Bill over the years. I retired 26 years ago after 34 years at Sikorsky. I didn't know too much about what his career was, but I kept in touch with him until he died 2 years ago at the age of 91. No, about a year ago, last March, sorry. That's one of the early aircraft. John? Now, the first outgrowth of this, and what I'm going to describe really is the development of a species. One aircraft growing out of the experience of a prior aircraft. This is a direct result of the S-50, of the R-5, the S-55. Now, of course, we realized that we could no longer put the engine directly under the rotor and have a very simple transmission system if we wanted to carry a variable payload instead of an observer, somebody looking for submarines. So this is what we did. Put the engine up forward, and the rest followed very nicely. We could put the variable load in the high real estate region right under the rotor, and it worked out to be quite a good start, but not exactly what we wanted. So when we came to the Navy request for an ASW aircraft, we took this design and enlarged it. Of course, we increased the power, and we came up with the S-58. Now, the S-58, I think, is much more familiar to most of you. It was a fantastically popular program, sold in the thousands. It was a fantastically easy development. We had no significant problems at all. It was quite unusual, like nothing. And the reason for that is that we had applied, we did not stretch our knowledge very far to go from our experience with the H5, with the H5 and S-55 to derive this design, another evolution of the species. John? Now this was a horse of another color. Came out at about the same time, around 1952. We were committed to the S-58. We had high confidence about the S-58 because we knew practically everything we had to know to pull it off. This one was entirely different, presented serious problems. We really had to stretch whatever we knew. And it was from this design that I reminded our management that we had scraped the bottom of the barrel of our information, our knowledge, our techniques, our ingenuity in order to pull this one off. Had two reciprocating engines and bubbles out the side. That's what they look like. It was what we used to say, it had a built-in headwind. But anyway, somehow or other, after some serious problems, we did manage to pull off a very practical, reliable helicopter, not so much for the Marines, who were primarily interested in it, in developing their idea of vertical envelopment, but for the Army as the H-37. This was not as successful as the 58 from the standpoint of the number that was made and the profit that was made from it, but we learned a tremendous lot. One of the things we learned was that we were very naive at the beginning. We had to hover at 6,000 feet, 95-degree atmosphere at normal gross weight. At the same time, we had to have a Vmax of 140 knots. That was a very difficult combination to pull out of the hat for a one rotor system. We had thought that all we had to do was increase the twist from 6 degrees to 12 degrees, take care of the hover efficiency, but that was not the case because we stubbed our toe very seriously from the standpoint of structures, vibratory loads and stresses on the rotor for the aluminum rotor were prohibitive. We could not continue with it. So we ended up actually not meeting that requirement, but we met the 140 knots because we had plenty of power. Now, I must also tell you that we had a machine that weighed over 30,000 pounds at that time. It was equivalent to the H16, but instead of having two 82-foot rotors, it had one 72-foot rotor. The reason for its size, physical size, was that it had to fit initially on one of the small helicopter carriers that were used by the Marines at that time. Now, the lesson we learned, and which hurt us for a while, we learned it the hard way, became later the lesson that the military learned by requiring a risk reduction program as part of a proposal. I went to management and said, in effect, what turned out to be a risk reduction program, I said, we have to do some research. We did not have a research program at that time. And so I was able to start with a budget of 4 engineers. When I ended up at Sikorsky, back in 1976, our engineering budget was over $20 million a year. And it was a little bit bigger than 4 engineers. And I understand now it's probably in excess of $150 million, something of that sort. Some of the later members of Sikorsky probably given a much more accurate estimate. That was the lesson. That was a very important lesson. Since that, the S-56, we had a continuous build-up and an ongoing research program in anticipation of the almost inevitable increases in requirements to be specified by the services and by the commercial people. Now, I turn to the earlier developments right at the beginning. I won't go on with this. This shows another further development of the species in the S-61. Again, building directly on the S-58 and the S-56. This ended up, eventually it ended up with the Black Hawk and a few other things like the S-64, the crane helicopter, and so on. But that is not really pertinent to this gathering. John, I think that would be the end of the biographs. At the very beginning, we had a small group, as Miller Wachs explained, of about 15 people. And I was very lucky when I joined Sikorsky. I had been with Brewster for several years, Brewster Aeronautical, which had they had the honor of making probably the most inept fighter aircraft for World War II. And I worked on that, and I also worked on their dive bomber. And I eventually drifted over into armaments and got a couple of patents on that, and as to how you very quickly change an aircraft engine, a machine gun barrel after a sortie. The Navy insisted I take a couple of patents on that. Brewster wasn't interested for some reason. Anyway, so I joined Sikorsky early in 42, luckily before they froze you in your job. And that was a couple of months later. I joined in January. I worked for Bill Hunt, first my mentor, my instructor, a very good British fellow, a very fine engineer whom I revere to this day, unfortunate in his career development to some degree. He had difficulties with our engineering manager at the time, and he had to leave. And I will tell you a rather unique story. I shouldn't say rather, unique after all is unique. And that is this, that there was the man appointed to be project engineer to replace Bill on the R5 happened to be very much disliked by the engineers who were going to have to work for him. I have no idea why they disliked him, but they came marching into the engineering manager, assistant manager's office and said, "We will not work for that man." So, big blow up. Igor went to the front office of the Sikorsky group, and they said, "Sorry, Igor, you have to solve that problem yourself." Now, Igor, I must say, was a very, very brilliant designer. But that's what he really wanted to do. He wasn't really the kind of person to handle personnel problems. So what was suggested, I forgot who suggested it now, was that we mentioned, our management should appoint or nominate 4 candidates for the job. And that is how it came about that I was elected to be the project engineer by the engineering department. I was rather, I was only 2 years up to that point, two and a half years in the aircraft business. I won't mention what I did before. I was working for a laboratory, and I was thinking of becoming a physicist, which I was directed away from by my thermodynamics professor, whom I also revered, a real grand old man of thermodynamics, and said, "People don't know today what a physicist is." And I was a very poor boy, and he said, "I know you have to make money, so be an engineer." And of course, I had always been interested in aircraft anyway, absolutely fascinated by them. And of course, when I was 11 years old, you know, symbols have a great meaning for children. And Lindbergh flew the Atlantic on my birthday. And of course, I was already fascinated by airplanes. So that's some personal ideas. Anyway, so we got started after the flying boat was finally canceled. And the fellow who was rejected, of course, naturally said, "Well, Katzenberger won't do it. He's a kid, and he's going to go flat on his face." Well, I was competing at that time with Ralph Alex. He was project engineer on the R6. The R6 was a development from the R4, a very much smaller helicopter. And we competed as to who's going to make the first flight, the R6 or the R5. Well, I won that competition. And this gave me a little more confidence than I had at the beginning. And as you all know, the R5 became the S-55. Now, I'll mention just one other thing to give you some of the, you might say, the local color of the business. We had a problem with one of our guest pilots flying the R4 who failed to push the collective down when his engine failed. Fortunately, he was close enough to the ground, and it was just the right height to be not quite in danger, but it was a terrible shake-up, and the airplane had a few minor things that came of that. So we were wondering now, what can we do to make the stick be pushed down when the engine fails? Obviously, we had to devise something that was sensitive to the engine, the engine goes out, automatically the pitch goes down, whether the pilot is daydreaming or not. So Jimmy Wiener, our chief test pilot, and I, we took the two doors off the side of the R5, put on seat-type parachutes, went over the Fairfield Marsh at 4,000 feet, hovered, and Jimmy pushed the throttle forward, and the engine, not enough to put it out, but to put the RPM way down. And we had a Grumman flap actuator actually doing the job. Well, we fell 600 feet before you could blink your eyes, but the engine came back. I mean, the pitch went down, and we went into auto rotation. So, of course, Jimmy gladly pulled the throttle back, and we went home. So that showed that that system could work, at least if we had enough distance between ourselves and the ground. We never went any further than that because it was never used, it was never considered really necessary, and we never did have another incident of a pilot daydreaming and not pushing the stick down. So that's how we left it. That's just one of the things we did. We did number of other things that are not quite as dangerous, but were rather interesting. Like the pitch throttle synchronizing linkage, for example, a little twitch in our little device in our control system, which gave us a better synchronization between the pitch of the rotor and the throttle setting on the engine. That worked very nicely first time out, and so it was used on all of our reciprocating models after that. I guess I've run out of my 10 minutes. So thank you for being attentive. Now going down is more difficult.
You're welcome. Thank you, Ed. A real pioneer. Ted Carter, you're next on our list. The timing is good. We're going to run probably a little beyond 5. I do have a couple videos, one on development of the Bell helicopter and one on development of the Sikorsky helicopter, and I'm willing to stay and show those, but you people are no obligation to wait around. Ted.
Well, I think it was very fortuitous that I'm following up Ed, because I want to add to what he had to say that I don't think he anywhere near gave himself credit for his contribution not only to Sikorsky but to the AHS. Number one, in 1950 about, when Sikorsky a year or two before had lost the competition, we built the S-53 and it was beat out by the tandem Piasecki. HRP1 was it? I've forgotten the numbers. And then Bell suddenly jumped on the tandem bandwagon and beat us out for the ASW competition with the Navy. Things looked very, very bleak for the single rotor helicopter. And Ed was the one who came up with the concept. The problem was basically that we couldn't compete CG travel-wise. We couldn't get our payloads from no payload to full payload and keep the CG where the rotor could manage it. And Ed came up with the concept of pushing that engine forward, as you saw on the S-55, and combined it with the offset flapping hinge. And the S-55, I'm sure you all realize, is what put the single rotor helicopter back in the game. On top of that, Ed didn't mention that he, in fact, was the guy who really started the AHS. He and a couple of other guys sitting around over dinner one day came up with the idea. I know there a lot of people joined him very shortly thereafter, but I think he was, Ed, weren't you the first interim president? Is he still here? That's right. So we owe him a debt, both from Sikorsky's point of view and from the point of view of the AHS. Now, I'm a little embarrassed to be up here. I think that I ought to entitle this probably Second Generation Pioneer, or perhaps he also serves who fills in the gaps. I joined Sikorsky in 1946. I'd taken aeronautical engineering with Nick Nikolsky at Princeton, but then the Navy sidetracked me into amphibs, and I'd been bitten by the helicopter bug, and so I grabbed a job at Sikorsky right after the war, worked for Jack Churn for a couple of 3 or 4 months, and then was recruited by another guy who has never had the credit that he really deserves, and that's a fellow named Walt Gerstenberger. And really, he should be giving this talk, because what I'm going to talk about are how I was able to implement the ideas that he came up with, and got a great deal of satisfaction out of my early career because of it. Walt was basically a one-man chief of dynamics, and I became his sidekick, initially a gopher, and later the guy to develop the technology base to do what he wanted to do, and eventually, essentially the project engineer on the HSS-1N that you saw in Don Sagner's talk. The 3 problems that Walt had me focus on were, number 1, vibration. Clearly, vibration was an insidious problem with every machine we were building and everybody else was building. And trying to develop some handle on where it was coming from, how you could mitigate it, was a high priority. I started on that about 1947, and I can remember sitting there with a mechanical calculator that you had to crank, and it did 1 digit at a time, and you could spend a week doing a single case of an iterative analysis to try to understand the mechanics of how the blade was interacting with the airframe to amplify the vibrations. We pretty quickly moved to a pragmatic approach of shake tests and the use of vibration absorbers. Initially, the thing that kind of bailed us out were cockpit absorbers. Later on, and by that time I'd handed this off to Ken Mard because Walt wanted me on something else, but things like the bifilar absorbers on the rotor heads that stayed tuned to the RPM of the rotor. But that was a real challenge, and it remained a challenge, I guess, for my whole career. However, the next job we had to face was a question of the control forces. You've heard a mention of that. Obviously, the S-51 was pushing the limit of size that could cope with control forces that came out of that rotor. A lot of people were working on ingenious solutions to try to work with the inherent mechanics of the rotor to reduce them. Walt was a brute force guy. He said, they may work them out or they may not, but in the meantime, let's just fix the problem. And he sent me over to Chance Vought to learn what they knew about hydraulic servos. And as a result of that, we got into hydraulics in a very big way, very, very fast. And I think pretty quickly we had scooped the fixed wing industry. By the S-55, the S-55, we had a 4 degree of freedom, all hydraulic, irreversible powered control. The fixed wing people were still working with boosts and limiting their dependence upon it. Of course, the key to it was it had to be reliable. One nice thing about my job was it gave me a little time in the cockpit from time to time, and I'll never forget the first time we took off with the hydraulic servos installed, and Jim Chuders, the pilot, didn't want to turn them on until he got in the air, and so he took off, and in a hover, I pulled the handle that threw on the hydraulics, and Jim thought the stick had broken off in his hand. He couldn't believe what he was dealing with. He got us back down on the ground and took a long breath and then went on to fly it very comfortably. But hydraulic servos were really what it took to crack that size barrier. And then the next issue was IFR. The fact remained that if we were going to really contend for military missions, we clearly had to have an IFR capability. And that all got back to the fact that the helicopter really was a challenge to fly. And we suddenly realized that we really had a unique beast in our hands. A lot of people were working with the inherent stability and devices to try to mitigate the tendencies to instability in the helicopter. But it suddenly dawned on us the real problem was simply that we had 4 independent degrees of freedom in a hover, and each one of them the pilot had to try to manage independently. It was like trying to pat your head and scratch your stomach and slap your heel and rub your knee all at the same time. And so even if we could improve the stability of each degree of freedom, the demands on the operator were going to exceed what you would expect him to do in something like a night ASW mission. As a matter of fact, it suddenly occurred to us that for the first time we were trying to build a machine that didn't necessarily go the direction it was pointed. If you think about it, most man-operated machines have that virtue. They're a point-and-shoot device. The helicopter is anything but a point-and-shoot device, at least in a hover. And so again, Walt pointed us to the brute force approach. He packed me off to go up to MIT and work with Renee Miller and kind of match what Renee could tell us about the equations of motion of a helicopter, the stability characteristics, with the feedback control techniques that the Draper Lab was developing. And I came at just the right moment because the Draper Lab had just rediscovered the root locus approach to analyzing control systems. And in fact, the reason I joined the AHS in 1952 and qualified for this session was because I gave a paper on the root locus of the helicopter. But we came back to Sikorsky, put together the first automatic stabilization system, and again it was a question of drawing on what fixed wing knew, but then running circles beyond where they were. We realized that the autopilot approach that the fixed wing people did, that removed the pilot from direct control of the vehicle and put him on some kind of a joystick that then talked to the electronics that then worked the airplane, was not going to satisfy the pilot who was hovering at night at 30 feet over the water. And so Walt was the one who came up with the idea of the limited authority differential addition to the control by which the pilot was still on the stick and in command of the situation, and he was getting the assistance with about 25% of the authority of the full stick to keep him doing what it was that he thought he wanted to do. That had its opportunities to get into the cockpit too, and that was fun. And those sometimes were scary and sometimes they were comical. I can remember the first time we took Michael Glurov, Igor Sikorsky's #1 sidekick, up for a demonstration of the electronic stability system, and he put his hand on the stick and jerked it off and said he got a shock from the electronics, and he never did fly a stabilized helicopter. Well, I know our time is running out, but the ultimate answer, of course, to that was that we did get the IFR mission on instruments, and of course that had a lot of derivative benefits for other missions. But it was a great time to be filling in behind you true pioneers who laid out the basics for us and gave us something to work with.
Ted called me up a few days ago and said, I'm going to bring another pioneer. Will you introduce your other pioneer?
Well, I have the unusual situation of being married to a gal who flew a helicopter long before I got into the cockpit. My wife, Ann, was the first gal in this country to get a helicopter license, so I told Ray I thought he ought to let her into the meeting, and he agreed.
Tony Paradiso, you're on.
Well, I anticipated this was going to be a session in which everything is getting cramped. So what I've done is I've planned my presentation just like designing a woman's dress. It'll be long enough to cover the subject, but short enough to be interesting. I will talk about the forum. Mainly, it's a celebration of a birthday. Then I will have a video, excuse me, Jack, which will show the evolution of the VS-300. In 1940, at the beginning of my career, I became a member of the Society of Automotive Engineers and the Institute of Aeronautics at the recommendation of my mentor. He was very active in the professional societies. The advantage of the societies was evident when I was having lunch with brown bag lunch with a group of the engineers at Sikorsky Aircraft. This was in the late 1942. I had mentioned that the societies have the advantage of giving the engineers and other professionals in the group the benefit of listening to speakers who are leaders in their field, who are sharing their knowledge and experience on current production programs, and also learning about the plans for future programs. It was in late 1942 that I was having brown bag lunch with a group of engineers at Sikorsky Aircraft that we initiated the idea of creating the American Helicopter Society. The meetings and the society began in 1943. In 1984, I had given the society my draft copy of the Constitution of the American Helicopter Society. This was at the 40th Annual Forum. And in 1950, at the 50th Annual Forum, I presented the American Helicopter Society with a 1/20th scale, museum quality model of the VS-300, which was the first practical helicopter in the United States. The model was not built from a kit. It was built from scratch by 3 model makers who were craftsmen, and they had spent about 600 hours putting it together. Sikorsky Aircraft provided me with drawings, photos, and videos so that the accuracy of the model would be assured. I have a video which I'd like to show now, showing the development of the VS-300. Among other things, you'll notice in one of the early drawings, there's a single rotor design. I said, it's that single-bladed rotor. Get sound on. Oh.
Just a slight technical problem here.
I hope what hasn't happened was I didn't remove this video when I checked my baggage.
You want to start it over again?
Yeah, start it over.
All right, we're going to stop and rewind. All right, now we'll start it again.
As I start to say, I didn't remove this video when I checked my baggage in at security at the airport, so I hope it didn't
Now we'll play.
take out any of the contents.
Oh, I was pushing it.
Factory in
Okay,
Freeport,
all right, here we go. Thank you.
Sikorsky had not only invented a working helicopter, he had created an industry. Today, Sikorsky is the largest designer and builder of medium and heavy lift helicopters in the world.
Trace the evolutionary development of the VS-300A. The film clips are from Sikorsky Aircraft Film Library. This Sikorsky engineering drawing shows a single main rotor and a tail rotor, based on a single rotor design which Igor Sikorsky conceived in 1930. First flight took place on September 14, 1939. The helicopter was tethered so that it rose only a few feet and remained airborne for only a couple of minutes for each flight. Each flight fulfilled 2 needs: test the helicopter and help train the pilot. As shown by the video clip, controls remained a critical problem.
But by late 1939, Igor Sikorsky had built and was attempting to fly the first crude form of his VS-300 helicopter. The VS-300 had a cyclic pitch main rotor and a vertical tail rotor to control direction. But learning to fly it wasn't easy.
You have to lift the aircraft off the ground, teach yourself to hold it off the ground, say a foot or 2 or 3 feet off the ground, and then teach yourself how to be able to control the machine so that it stays within more or less 1 or 2 feet. That was the secret.
Part of this delay was caused by an incident on December 9, 1939. Serge Gluarev was the pilot. Stability and control were still very limited. A simple, unexpected gust of wind was too much. much to deal with. Serge Koulourev was not injured, but the VS-300 was.
There were major design changes made through the winter of 1939 through the spring of 1940. Flight testing resumed by May 1940. Now, note the extensive modifications made to the rotor system in the aft end of the helicopter. The single rotor was replaced with 2 horizontal rotors and 1 vertical rotor.
They decided to try this arrangement first with the machine mounted on a swiveling stand on the ground without having the main rotor installed at all. Here you see Mr. Sikorsky testing it out. And it seemed to work fairly well. This type of control was put into operation in March of 1940.
I stated earlier, I joined Sikorsky Aircraft in April 1941. On May 15, 1941, I saw a historical event. Igor Sikorsky piloted the VS-300 to a world record flight of 1 hour, 32 minutes, and 26 seconds.
In April 1941, Igor tackled the world helicopter endurance record with the VS-300 in this configuration. Igor Sikorsky's new world record was 1 hour, 32 minutes, and 26 seconds.
In August 1941, the tail rotor system was modified again. The 2 horizontal tail rotors were replaced by a single rotor mounted on a tower. This design change restored partial cyclic control in the main rotor.
Les Morris's first flight with the new control layout was a revelation. He was able to do forward runs of 70 miles an hour, quick stops, backup, and do things they'd only dreamed of with the old system, and no problems developed. Even so, Igor Sikorsky decided that this was not the right control system for the new Army helicopter, the Sikorsky XR-4. And since the VS-300 was the test vehicle, it would be modified to test the next stage of control development.
The horizontal tail rotor was discarded to return full cyclic pitch control to the main rotor. Full cyclic and collective control in the main rotor was achieved on October 1941. The final configuration of the VS-300 made its first flight on December 8, 1941.
You've probably played with a toy like this, and you know that if you spin it in the horizontal plane, it will rise and descend vertically. Tilt it to the right, it'll fly to the right. Tilt it to the left, it'll fly to the left. Forward, backward. That is the basic concept of helicopter control. The problem was how to accomplish the tilting of the main rotors. Sikorsky's design of the VS-300 helicopter introduced cyclic pitch control for the first time in a single main rotor helicopter. It's still the type of control that's used almost entirely, or perhaps entirely, in all helicopters throughout the world. The pilot has in front of him a stick called the cyclic stick, and whichever way he moves that stick, the helicopter will tilt, forward, backward, or sideways. But how does he get the helicopter in the air in the first place? Beside him, in his left hand, there is a collective pitch control lever. We've talked about the cyclic pitch where the blades change their pitch in the cycle. The collective pitch lever changes the pitch of all the blades together or collectively. And naturally, the higher the pitch, the more the helicopter will rise in the air. At the end of the collective pitch lever, there is a throttle control device, usually in the form of a motorcycle type throttle grip. The pilot will adjust his engine speed by turning the throttle until he gets the proper speed for takeoff, and then he will pull up on the collective pitch lever, and the ship will rise off the ground. To come back down and land, he reverses the procedure. He lowers the collective pitch lever and maintains proper engine speed, of course, by adjusting the throttle as necessary. Flights were made forward, backward, and sideward, and no wobble or resonance was detected. Thus, on the last day of 1941, the VS-300 demonstrated another completely satisfactory control system.
At last, they had it right. The classic Sikorsky configuration had arrived. A single main rotor with full cyclic control and a small vertical anti-torque rotor with variable pitch. Sikorsky's dream of unlimited freedom of transportation was within reach, but he also saw the helicopter as a means of saving lives. Now, with control problems apparently solved, there was no limit to what might be achieved. Igor Sikorsky had indeed taken a chance to live his life over again. For the second time, he had built a flying machine without knowing how, and had taught himself to fly it. This was the final version of the VS-300, the culmination of 3.5 years of development. The name was still the same, but not much else was.
The recapitulation for the year written in the flight logbook tells the story. During 1941, 3 totally different types of control were investigated on the VS-300 with a total flight time of 28 hours, 35 minutes, and 55 seconds.
Let's see what might happen someday after the war is won. You come out of the grocery store, bread, milk, steak, yep, that's everything. Back to the parking lot where you keep your helicopter. Routine by now. Load up the luggage basket. Put on your coat.
Just about I like.
Oh, good boy. Just like the old days of automobiles. And take off for home. An honest day's work done. Logical. Here we see the VS-300 snugly tucked in between some automobiles. How did it get there? The truth is it flew in. And if you don't believe it, watch this. Here is one of the most dramatic examples of the helicopter's ability to operate in restricted space. Please notice that the camera does not once leave the aircraft as it circles in a 360-degree shot. Please notice, too, that the parking lot is solidly lined with automobiles. When veteran pilots see the maneuver about to be carried out, they open their eyes wide, their mouths even wider, and then they grin and say, "Doggone it, I still don't believe it." The helicopter returns and hovers over the space it occupies, which you just saw it leave. It returns, it hovers, and it settles down squarely in the middle. A better parking job than you usually do with your car.
The VS-300A is shown here at its permanent display at the Henry Ford Museum. The person by the helicopter is Les Morris, the first test pilot of Sikorsky helicopters. Sikorsky helicopters. Pouring coverage.
Very good, thank you.
Thank you.
Got 2 more on our list. Now, but both of these and myself and actually Tony are from California, so it's early in the afternoon. So we don't have a time situation. But Bob Bosler, you're on next.
I figured I wouldn't even speak. I was quite on the list. I gave Ray a little write-up of where I was 50 years ago and what I was doing. But I got to thinking about my checkered career here, and I wrote down some numbers of what all happened. And basically 51 years. First 5 years were at Bell. The next 23 were at Command. Then I went to Lucas Western for 15 years, which was formerly Western Gear. And then I've been a consultant for the last 8 years, and the work has not stopped. I told Ray, we're all of us supposedly retired, but none of us are. And I turned in my last report to the Army in February, and I've been busy on other things since. My work has included design, analysis, manufacturing, test, and production. In other words, it never stopped. Now, in addition to that, I was able to perform and supervise research contracts for 7 government agencies. They claimed that when I was at Command, I was the first one to discover you can work on anything you want to work on. You just have to sell it to somebody. Well, I never had trouble coming up with ideas that I thought needed worked on. I produced 4 documents for the SAE and helicopter power plants. And I've been awarded 20 patents and I've written 35 technical papers. So it's been quite a survival, and it's been very interesting. I got contribution awards from NASA and SAE, and I don't think I'm through yet. My ambition now is I'd like to write a book on great ideas I never got to use. There's plenty of them around. That concludes my little discussion. Thank you.
Norm, you're going to wind this session up here. But after Norm does this, what we're going to do is all the pioneers are going to get up here, and we're going to get our picture taken. So the pioneers don't go away after it. And then we're going to take a 10-minute break, and I'm going to show you the video that Bart Kelly made on the birth of the Bell helicopter. It takes almost an hour, so we'll do that. As I say, for Norm and me, this is still early afternoon.
Good evening. Excuse me. I'm honored to be here for talk as a pioneer. I think it was very considerate of the society to have me here on this very day of the 55th wedding anniversary of my wife and me. Okay, hear me better? My first engineering position following college graduation in 1949 was at Wright Air Development Center, Dayton, Ohio, under Bernie Lindenbaum, who was a great mentor in this field of rotary wing. There were several projects that I worked on in the couple of years that I was there before I had to leave for family responsibilities in my home city of St. Louis, Missouri. Developing good methods for performance evaluation at that time was particularly important in light of the subsequent programs that would be evaluated. A very important program that I worked on at that time was the performance evaluation for the proposals for the Arctic Rescue Helicopter competition. In that particular competition, the Piasecki vehicle was awarded the contract of the event, and it was identified as the H-21 at that time. In addition, one of the programs I got to work on was the long-range helicopter tow program for purposes of air rescue. Now, at that time, the helicopters operated at very low altitudes, and one of the problems we had was finding a drogue to which the helicopter could make an attachment. And as a result, we actually had two parts of the program. One was to find and demonstrate the drogue, the applicability of the drogue, and another was to actually tow a helicopter to a point of rescue, at which point, if the operation with the drogue would work properly, that it could be released and go down, make the rescue come back up, attached to the drogue, and be towed back. I happen to be the living recorder, motion picture recorder of the drogue operation. I would be placed in a C-47, held in place looking out of the door at the rear side of the vehicle, and held in place on the floor by the crew chief sitting on my back. There were a number of drogues that were tried. Flying at the lower altitudes, we had a lot of gusts that would not occur at the higher altitudes where normal air refueling would take place, but Bernie did come up with a drogue that was fairly successful. And I would observe a number of pilots, one after another over a period of time, who would attempt to contact the drogue, maintain contact with it for 20 to 30 seconds, and then fly freely from it. Of the many pilots, at least 5 that I remember working with, there was one pretty outstanding pilot, Wayne Eggert, who made contact under the most gusty conditions and maintained the probe from the helicopter on the drogue and just flew right with it. He would stay with it 20, 30 seconds, move away, and start over again. And there was nothing that could keep him from making contact with it, and he was simply flying an R5 or H5, whichever it was at that time. As far as the tow portion of the program, 4 or 5 pilots had tried or had made they had been towed behind a vehicle. It couldn't be a CH-47 that didn't have enough power to pull an H5, but they tried with a CH-54. And the procedure would be to take off from the starting point where the helicopter pilot would hover and take up the slack in the cable as the C-54 would move forward and take off. Well, 4 or 5 pilots did that very successfully, taking up the slack. Then when they were finished, a pilot in the project office who hadn't flown helicopter for a while was asked if he wanted to try it. Well, he got up in the air and he moved along with the transport when he realized that he hadn't taken up the slack. And he allowed the slack to be taken up very quickly. The cable ruptured, flew back into the rotor. He was only about 500 feet off the ground, and that was his demise as well as the helicopters. That program was followed by further developments. Bernie Lindenbaum came up with a solution to the snapping of the cable by having a weak link at the near the forward end of the probe, so that if it did snap, it wouldn't go back up into the rotor. But again, I had left the area at the time before it really was proven successful. However, that was in the like 1951, and in 1970, one of the supervisors where I was working, at that time it was at Lockheed, came to me and asked if it would be a good idea to use one of the analyses that they used, that had been developed at Lockheed, for doing an analysis on the tow program. My comment was that that's a case of overkill. There was no need to use that kind of analysis on this particular job. But the thing that really surprised me was by that time, helicopters had been flying higher. They'd been flying they were refueling as conventional airplanes were. In fact, I think there were several Sikorskys that flew across the Atlantic having refueled from refueling aircraft. But that was the end of that aspect of my experience. Subsequently, when I went back to St. Louis, I went to work for McDonnell in St. Louis. And one more thing about Wright Field. Working there as a young engineer, I had the opportunity to meet the upper-level engineering and management of the various companies. Ed Lightfoot came through from Sikorsky. He greeted me as Mr. Gorenberg. Frank Piasecki would come through. How do you do, Norm? I mean, really, very cordial, very outgoing. Then I was, one day, Bernie comes by and said, how would you like to, or Norm, I'd like to introduce you to Bart Kelly of Bell Helicopters. And I was really thrilled with it. And I said, hello, Mr. Belly. I don't know what he called me after that. But in any case, it was shortly after that that I went to St. Louis and I started to work with McDonnell Aircraft. And shortly after I was there, they had won one of the 3 awards in the converter plane competition. The other 2, I think, were Sikorsky, and definitely the third was Bell with the tilt rotor. A good portion when I worked there continued on the XV-1, and I had gone to Wright Field to test the rotor on the world stand there. I had the experience of meeting Stan Martin, who was there on reserve duty in the Air Force, but he normally worked with Bell Helicopter, and there were many times I couldn't be sure that I was working at a Air Force facility or a Bell facility, considering the questions that Stan would ask me. But he was a very friendly guy. But we kept up a friendship for some time. But again, when we had to turn in a report on that operation, where I had tested the rotor on 2 separate occasions for 1 month at a time, the questions I got from Stan again made me wonder who he was working for. In 1959, the work on the XV-1 had been completed as far as what the Army or the military wanted to learn from that configuration. And McDonnell himself was interested in getting into transport aircraft as well as space operation, because his entry into the field had been with fighter aircraft such as the Banshee and the Phantom, and he was eager to expand into these other areas. And in 1959, when the Army was going to do its own examination of vehicles, what had happened was that up to that time, the Air Force had been evaluating rotary wing aircraft for the Army, and at that point they were not going to do that any longer, so the Army had to get in on its own to do all that. And they went through a whole series of tests of various aircraft. McDonnell maintained a corps of helicopter engineers, but he also sent a number of them to other divisions. In fact, one of the early local chairman of the Helicopter Society was very much interested in space, and he went off to work on the Mercury capsule, in contrast to staying with rotary wing. I had I definitely wanted to stay in rotary wing. I could see working on these other things for a while that would keep me employed. But meanwhile, I had inquired at VTOL, which was at that point an offshoot of Piasecki. I was interviewed by Bob Lowy, who I saw here earlier this evening, and I was employed there. The point was that VTOL had just won the competition for the CH-46, which was a sea night. And when I arrived there, the company had been under pretty dire financial straits. It looked like a dilapidated dump compared to what McDonald had looked like in St. Louis. In fact, the engineers were emptying the trash cans in the restrooms because they'd let all the custodians go. But within a year, Boeing picked up VTOL. Now that was a real mixed blessing, and I'll explain. The engineering help were in Seattle, we were in Philadelphia, were really great. They did everything they could to help us. We had the access of their new IBM 7004 computer with which we could saturate any helicopter problem compared to fixed-wing aircraft. The wind tunnel in Seattle was made available, or one of many wind tunnels in Seattle was made available to us, and I would go out on a 2-day test trip and get there, sometimes finding that somebody in the fixed-wing part of the company had priority, so my 2-day trip would end up 2 weeks. Sometimes a 6-day trip would end up close to 6 weeks. But in any case, during the day I had access to their computer. The testing was done on the swing and graveyard shifts when electricity was cheaper, and that went on. I came back, I guess it was early 1962, and I was told that I'd used up all the research funding for VTOL for that year. And I said, how could that be? I didn't use the number of test hours I had. I got my costs from the finance people before I went. What happened? Well, I checked into it. They had forgotten to include the overhead, which is 2.5 times the price of the basic testing. Anyway, within a month or so, I was sort of pardoned on that, but we had also had recs out for some 6 people in aerodynamics, and we had already arranged for at least 2 of them to come who had sold their homes. I came to work on a weekend there to do some local catch-up time before the next week starts, and I find a number of Boeing management people there in the company. What the heck is going on here? Well, Monday morning I found out. They came through, so we couldn't hire these 6 people that we had recs out for. And we explained that 2 of them had already sold their homes, that we were ready to bring them in. Well, you could bring those guys in, but forget about the rest of them. But of the people you have working with you, Norm, which were 6 associates, I had to let 3 of those go, which wasn't a very good situation. Well, it developed that 2 of them, for personal reasons, were planning to leave anyway. So I was down with possibly 1 more that I had to let go, but they allowed me to keep him. But here was a company that had maintained a very low cost of operation for several years practically until they got these contracts. And here, Boeing Finance was going to show them how to save money. Well, that was pretty ludicrous at the time. And I had heard of what was going on at Lockheed, bits and pieces, of course, for a while, and Kurt Hohenemser, under whom I worked at McDonald, was particularly interested because in the early stages of that effort at Lockheed, from what he heard, that much of the gyro operation was associated with a varying RPM, at which point he didn't have much confidence in it. But when they came in and started working with a fixed RPM, his appraisal of it was much better. And so I thought I'd make an application out to Lockheed. The first person that contacted me after I made the application was a fellow by the name of Paul Theriot,